Okay, so that's great. That's great. So, very good morning to all. And first of all, I would like to once again thank to Dr. Shashi Shekhar Jha from IIT Ropar, Department of Computer Science and Engineering, for kindly accepting our request to be a part of a FDP as a speaker. In a very short moment of time, he said, okay, I will go ahead with this one. And definitely, sir, we are very lucky enough to have you on this FTP as a speaker. And I would like to give a brief introduction about Dr. Shashi to all our participants who are on the Zoom as well as on the YouTube live streaming channel. Dr. Shashi Shekhar Jha is presently, he's working as an assistant professor in Department of Computer Science and Engineering at IIT Ropar from 2018. He has worked as a research scientist in Fujitsu SMU Urban Computing and Engineering Corporation Lab at Singapore for 2 years. He was a postdoc research intern at Accenture Technology in Bangalore. He's a supervisor. He's a degree research supervisor in Swinburne University of Technology in Australia. He did his PhD from IIT Guwahati. And his area of interest is artificial intelligence, multi-agent system, multi-robot system, and reinforcement learning. He has very good publication in very, very reputed, highly reputed international conference and reputed journals. He has one patent which is being granted to him. And his scholars are really doing wonders. Some are having some TCS fellowship and some are pursuing PhD in Swinburne University, Australia. He's a winner of $9,000 prize money in some open task challenge. And he was also in TCS from 2013 to 16. He has been invited for many talks at a national and international level in most of the IITs and IITs in India, as well as in Taiwan and other countries. And definitely the experience of industry, the experience of lab, the experience in academics, definitely it will help a lot of in academics to all of us, especially those who are under his guidance or those who are his students in IIT Ropar. And definitely I had already attended a one FTP being organized by Sir in IIT Ropar, and that was really a wonderful FTP where I learned a lot of emerging things which is happening right now. And deep reinforcement learning has really a wonderful application, mostly when we are talking about 5G and 6G, software-defined networking. So in that case, the deep reinforcement learning has a wider application. And recently, one day ago, I just went to the thing that because of the 5G launch in US, most of the flights have been cancelled from India to US because of the interference in communication may happen. So in this regard, definitely, sir, your talk will be wonderful. So once again, I thank you all. Thank you for coming and accepting our request, sir. Please go ahead, sir. Please go ahead. It's over.
Okay, thank you. Thank you for the wonderful introduction, Dr. Ashok. And welcome everyone. I hope everyone is safe and sound and taking care of yourself and your families and taking all the necessary precautions. So I'll just load my screen now. Right, that's my screen. Oops. Yeah, just let me know if it is visible. And Dr. Ashok, how are we taking questions during the session? Like,
no,
is there any way?
the questions will be on the chat window, and even in the live streaming, what are the questions we will be putting on the chat window if there is any.
Okay, great.
Thank you.
Okay, so if that's the mode, then all the participants, maybe you can note down your question and I can take all your questions, towards the end of the session, right? So I think that will be better. Okay, so with that, let us start today's discussion. So I say not a lecture, a discussion. So we are going to hopefully discuss about this topic called reinforcement learning, where I'm spending a lot of my time in last 2-3 years. And I'm really excited about this area and all the great algorithms that are coming in this area. So I'll introduce you to a few of them today. And let's see if I am able to arouse enough motivation in all of you, and help, maybe you can look into reinforcement learning and more techniques into it, and maybe if some of you are interested in research, then definitely we can connect further. So with that, as Dr. Ashok mentioned, my name is Shashikhar Jha. I'm an assistant professor at IIT Ropar. So the background that you see is the IIT Ropar campus. So if you're in Ropar, do visit us. Okay. Right. So since we are going to talk about learning, why not we start with a basic definition of learning, or what do we understand as learning, right? Now here the learning is with respect to machines, or machines is again a broader term nowadays, because there's so many things in machines. So by learning now, this is with respect to algorithms, or maybe with respect to computers. So what do we mean by learning, right? So I have these two thoughts about learning, and like maybe this today's discussion also focuses on these two aspects of learning. So first is making machines more adaptive towards a task. So here two important things are there. One is adaptiveness, and another thing is task is actually has become very important for learning, right? So there is this idea about artificial general intelligence, and learning about anything. But currently all the learning is basically focuses on something called a task, right? So for a task, we train an algorithm to learn, right? And how do we learn then for a particular task? By providing more data as experiences. So that is what we mean by learning, or learning with respect to machines or computers. And second is providing the ability to learn and improve from experiences without explicit programming, right? So that is another aspect of learning that we want to have, where given a basic algorithm, maybe the computer or the algorithm or the program, right, they starts improving. And by improving, we mean that as they collect more and more data, or as they do more and more interactions with the environment, right, their performance goes up, right? They learn maybe few rules, or few patterns in from the environment, from the system, that was not already present, and there's no explicit programming that was done. So this is how we understand as learning, right? Now specific to learning, most of the learning methods, they club together into this domain called machine learning, right? And many of you might be aware that when it comes to machine learning, there are basically two types of, usually people say there are two types of machine learning tasks or machine learning methods. One is called the supervised machine learning methods, another is the unsupervised learning methods. And then how do we actually segregate or differentiate? Many people will say, yo, supervised machine learning means there's labeled data, right? And unsupervised learning means there is unlabeled data, and then you have methods. But I would like to differentiate them based on the task on which these methods are trained, or are used. Okay, so supervised learning methods actually are well suited for classification or regression kind of task, and then there are multiple tasks in that domain that is mentioned here. Even there are more tasks like that, but supervised learning methods will focus on classification kind of tasks. So wherever there is a classification task needed, supervised learning methods will fit there. Similarly, unsupervised learning method are more suited for clustering kind of task. Okay, so the task here is clustering. Our today's focus is actually on these third kind of task, or third kind of method, which is called reinforcement learning. And what is the task here? The task is usually called control task, okay, which is different from your supervised learning task, which is classification or regression, or unsupervised learning task, which is clustering or dimensionality detection. So what are control tasks, right? And why, like, first thing, can we learn in control task, and what do we learn in control task? So I think I have few examples, right? So I have actually put 3-4 videos for you to understand what I mean by control task. If you see, there are 3-4 tasks here, right? There is a humanoid which is trying to learn to walk, and there is a quadruped here, which is like a spider, again trying to learn to jump and walk. And then there are robots playing soccer, and there is a robotic hand, right? Putting all these stone pieces from one above the other. If you see all these tasks, they don't actually fit into the domain of classification or regression, right? You're not classifying or tagging labels here. and they neither fit into this domain of clustering, right? You're not actually, you have the data that you're clustering. So these are the third kind of task where you're learning controls. Okay, so what do we mean by learning controls? Which action to perform in every situation, right? So there are different situations for all these four scenarios, right? And what is the correct action to perform there? This is what we want to learn. And this forms the control task. Again, these are only examples. There are many more. So I have actually listed a few of the applications of reinforcement learning. So different varieties of control tasks for you, right? Just to motivate you that, what is the all the domains where RL methods can be applied. RL means reinforcement learning. Okay. So like if you want to control a UAV, right? So if you see on the right hand side, this picture, it is an helicopter. It is also known as Stanford helicopter, right? So if you have not seen a video on Stanford helicopter, go on YouTube, search for something called Stanford helicopter and watch that video. So it's a like it's like a UAV. So it's an unmanned helicopter which is flying upside down. So the propeller is here on, and this helicopter has been trained using reinforcement learning. Similarly, autonomous driving or self-driving cars, they use a lot of reinforcement learning methods because those are control tasks, right? And robotic control, I just shown you in the last slide. But it's not only these very hardware kind of tasks, right, where you need control, even soft tasks like managing an investment portfolio or online advertisement or control of smart grids, right? There also you need to decide what action to take at every situation, right? Usually we refer situations as states in reinforcement learning. Okay, so what action to take in different kinds of state, that becomes a control task. So even you can have soft control task as well. Okay, there is one thing to note. So some recent superhuman kind of performance shown by reinforcement learning are these, like defeating the world Go champion. So it's been now little more than 5 years, right, when Google's this program called AlphaGo defeated the world Go champion. Go is a board game which has a lot of state space, right? 10 to the power 140 kind of state space. So it was a big deal, right? And a lot of enthusiasm then came to looking into deep reinforcement learning methods from that point. So that was a great achievement. And again, they improved it further on Alpha Zero and so on. And even in 2020, the same group, they came up with an algorithm that can predict protein folding for all types of protein that are available out there, right? So these are some recent achievements, and those algorithms can come. And today we are going to discuss or touch upon at least one of these algorithms, which is the first one or the most basic one. So with that, now we will delve into reinforcement learning, right? So I hope I'm able to motivate you enough that why we should look into reinforcement learning, or why should we even talk about reinforcement learning. Okay, so you can see the applications are a lot. So this slide shows the typical setting of reinforcement learning. So in reinforcement learning, you usually have an agent. Okay, so this agent is your algorithm, your computer, your program, your code, whatever you want to call it. Okay, so in reinforcement learning, we are going to refer it as an agent, right? And this agent has, sorry, this agent has a set of actions with itself, right? So like for your self-driving car, right? A self-driving car will always have a set of actions. What would be the set of actions for a self-driving car? Well, the action could be steering the wheel. The action could be brake pedal, accelerator pedal, changing the gear, right? And maybe, indicators on and off and all those. So these are the actions that are available to the agent. What is the task? The task is the agent has to decide, okay, which action to execute, and where do you execute the action on the environment. So there is always an environment available where the agent will execute the action. Okay. And in turn, the environment will provide some reward to the agent. Now, rewards could be positive and negative. So we don't call you, we don't want to use two terms, one reward and another is penalty. So we just use one term, reward. And if you want to refer or give some penalty for the action, you just give a negative reward. Okay. So rewards could be positive and negative. Rewards are simple numeric values. These are numbers. And what does these rewards tell? They tell that how good was the action on that particular situation, right? And one more thing happens here. Once the agent executes the action, receives the reward, the state of the environment also changes. So whatever was the previous situation, right? So it was like if the self-driving car was moving, right, and brake paddles were applied, right, then the situation is going to change, right? So we say the state of the environment is going to change. So the new state of the environment will be maybe the car has stopped. Right? That's the new situation. That's the new state. So the environment after the application of action provides rewards and also provides the state, the new state of the system. The agent takes these as inputs, you can say, or maybe observe these, observe the new state, and observe the reward, and then makes the next decision. So this is a setting, right, where what is the aim? The aim is agent should learn the best actions, the perfect actions are again from the available set, right? From its own capabilities. It cannot perform like a self-driving car suddenly will not fly, right? So that action is not available. So among the given set of actions, which is the best action in every situation? That's the aim, right? And that we want to learn. Okay, so the reinforcement learning methods is about how shall we decide an action for a particular state, and the only thing that we can use to make those decisions is these reward signals. Okay, again, these reward signals, as I told you, are provided by the environment. So environment is the judge here, right? So environment evaluates whether your action was a good or a bad action and then gives you some reward. So to receive that reward, obviously you have to encode it in some kind of a function, right? Based on all the state parameters, whatever the changes happened, and then we use that in our algorithm. So we'll see how the agent learns the best set of actions. Okay. So now let us discuss a few elements which are very important in order to make that learning. So first thing is called policy. And what is policy? Policy is again a function that describes agent's behavior. Okay. Now, how do we describe anybody's behavior for that matter? Leave agent. How do we describe a human's behavior? Usually, you will find that people will say that as anybody's behavior is described by the actions they perform. Right? You observe what actions people do, and then you make a judgment about their behavior. Same is true for our agents in reinforcement learning. Okay. So a policy defines agent behavior. That means a policy function maps states to actions. Okay, so if you have a function that maps or that tells you what action to perform in a state, we call that function as a policy. Right? And so what does policy will tell us? In every situation, which action to take. Okay. Now, if you go back to our earlier objective that the agent wants to take the best action in all the state. Okay. And we try to map that definition here onto policy, then the agent's objective simply changes to finding a optimal policy. Because policy is maps states to action. Now, an optimal policy will map states to the optimal actions, right? The best actions, the optimal actions. Right? So that's why policy is a very crucial element of reinforcement learning, or policy is the core of reinforcement learning, because now the focus is to learn this function in an optimal manner, or to learn the optimal policy function. Right? And second important aspect is definitely the reward. And what does the reward tell us? Reward tells us that, okay, what is the immediate judgment about an action? What is the immediate effect of an action, right? What is the immediate value of an action, right? So as soon as you apply the action, some rewards are generated. Okay. Now, if we so we apply the action, we get the reward. And if it is a negative reward, then that means that action was bad. If it is a positive reward, that means the action was better. And if we have even gradation in positive actions, then more the positive reward, that means we'll say the action was even better, right? Now, that optimal policy objective that we just described in the last slide, right? If we try to map that objective onto the reward, okay, Just think about it. Now we are saying that we are trying to map the optimal policy objective of the reinforcement learning onto something that we are receiving from the environment, which is the reward. Then if the agent is executing the optimal policy, that means the best action in all the state, then it will be receiving the maximum reward always, right? Because it is executing the best action. Okay, so if we just look into the reward and again try to reformulate our objective, then we can simply say that the agent's sole objective is to maximize the total reward it receives over the long run, right? Because once the agent executes an action, it will go to next state, again it will execute an action, go to next state, and this will sequence will go on, right? So if the agent is receiving reward every time it executes an action, and we focus on maximize the total sum of reward, right, that will automatically make the agent to choose the best action in all the state and giving us the optimal policy. Okay, so I hope you are able to make the connection between reward and policy, which is important here, right? And which is very important for our learning task. So we are trying to define here, the learning task itself before going into the methods. So here this is a very interesting slide that I like, right? So here, this slide actually tells you about the connection between rewards and policies. Okay, you see, we are considering a grid task. So this is a grid, right? It's a 4x3 grid. And there are two exit states in the grid, right? One is a +1 state, another is a -1 state. So at +1 state, the agent exits the grid with +1 reward. At -1, it exits the grid the -1 reward. Okay, and the aim is to maximize the reward. We want to get the maximum reward, which is the +1 here. So whenever we put an agent in this grid, we want the agent to receive maximum reward and exit the grid. That's the task here. Okay, now you see underneath each grid there is some reward function written, right? This is what we call living reward. Living reward means in all other states, in all other grid cells where the agent can move, this is the reward that it gets whenever it executes one action. Okay, and there are only 4 actions allowed: up, down, left, and right. 4 actions are allowed. So you see these are different rewards, different living rewards that are available. Now, if you observe, so what has been plotted in these arrows, you see this is the optimal policy that the agent has learned under these settings. Okay, and if you see this this cell, right? Well, this is 1x4 cell, right? So if you see this cell right at the bottom right corner, okay, the optimal action of the agents are changing. In the first one, the optimal action is to hit the wall, because if the agent is going down, it will remain in the same state, where the aim is actually to exit this grid from this +1 state. And if you see here, suddenly the agent has learned that it should go towards the left. Okay. And if you see here, the last one, the agent decides that it is the best action in this state is to go directly to a -1 state and exit. How come? Given everything same, board is same, actions are same, exit rewards are same. What is changing? This living reward is changing. And based on the living reward, the best action that the agent is deciding is also changing. Now, why that is happening? Well, it depends what the agent can afford in these environments. So here in the first one, if you see, the living reward is -0.01. Okay, -0.01 is actually very small compared to +1, right? So here what the agent does is, oh, I forgot to tell you one thing. Sorry. Okay, one thing I missed, which is about this noise here, which is mentioned. Okay, so this noise tells that although 4 actions are allowed, okay, but like the environment is little slippery, we can say. Okay, so whenever the agent takes an action of going up, going down, going left, or going right, only 80% of the time it actually goes up or goes down or goes left or goes right. Okay, and there is a 10% chance that it may slip towards left or right of that intended action. Okay, so if it is trying to go towards the left, there is a 10% chance that it may end up in this state or in the bottom state, if there is a bottom state. Okay, so because of this noise, okay, the behavior that the agent learns are different. Okay, in the first one, it learns a very safe behavior. Why it is the safest behavior? Well, the aim is to maximize the reward. That means we would like to avoid this -1 state at every cost. How to avoid this -1 state at every cost? Well, if you see, if the agent is just hitting the wall, out of 10 hits, there will be at least one chance that the agent will switch to this state because of this noise in the system. Okay. However, if you see, when the system or the living reward has become more negative, there's more penalty to execute even one action in the environment, the agent has started taking a risk. Okay, it is taking risk because while the agent is taking the left action, there's always a 10% chance that it will end up in this -1 state and get a very negative reward. But it is taking that risk because the environment has become very negative. It can no more afford to, just hit the wall and wait. And you see, when the environment is very negative, like the reward is -2, the agent decides that, it is optimal or it is better to get a -1 reward and leave the system instead of to execute any more actions into this environment. Right? So the reward function plays a vital role in the kind of policies or control laws or the behaviors your agent will learn. Okay, if the rewards are not well crafted, not well formulated, then it will not convey the correct message to the agent to learn the correct policy. Right? So that is what I wanted to build here. I hope you are able to see the connection between how rewards affects the final policy that you're going to learn. And again, so obviously then formulating the correct rewards or receiving or collating the correct rewards from the environment is not an easy task, right? So a lot of research goes on in something called reward shaping. You can check that out. So I hope with that, we have formulated our problem nicely. Now we understand what does reinforcement learning methods aim to achieve, right? What is the objective involved, right? So once the objective is clear, what are the methods available? So there are two kinds of methods, mostly in RL. One is called a model-based method, and another is called a model-free method. So what is the basic difference between model-based and model-free? So when we assume that the environment behaves in a certain way and we know the probability distribution of the environment itself, that means given the current state, right, given the current situation, and given the action that the agent is going to perform, right, if we have what you call a transition function, right, for the environment, that means what is the probability that from this state with this action the agent or the environment will move to any of these next state. If that probability is available, then we call it a model, or we call it the model of the environment is available, and all those methods that assume such a probability is available. Like in our this example, like this noise is basically a probability distribution. So the model of the environment is available, and because the model of the environment is available, we can use these model-based methods. But again, such probability distributions about the environment are very difficult to get. Okay, so all those methods that don't make any assumption about such models, that there is some model available, but we don't have access to it. There is always a model that is assumed. Okay, otherwise you won't learn or your methods will not converge. But if you don't have access to those those methods that focus on those aspects are called model-free methods. Okay, and then within model-based method, the two famous methods are called policy iteration, value iteration, and model-free methods. I think the most famous methods are temporal difference methods, and within temporal difference, Q-learning. So if you have ever heard about reinforcement learning, you must have heard about Q-learning. So this is a very interesting method which combines the benefits of these dynamic programming methods, which comes from model-based techniques, and also this temporal difference method that comes from model-free methods. Okay, so in today's session, like among all the methods that are available, we are actually going to focus on this Q-learning method. Okay, we'll see what Q-learning method, how it executes and how does it learn. It's actually a very simple method. Once we build this understanding, you will be able to very quickly get what is Q-learning. Now, other than these model-based and model-free methods, there is another category of methods in reinforcement learning called value-based method, actor critic method, and policy-based methods. So what are these? I'll just give you a very brief introduction about these methods. So value-based methods focuses on something called a value function. We're going to define what is a value function in the next slide. But these value functions are basically made up of your rewards that you're going to get. So, how did we define our problem? We said that we want to maximize these sum of rewards in the long run. Okay, so if we collect that sum and we say that for every state we're going to define something called a value function, the value of that state, and the value basically would mean that starting from that state, if we ever go into the future, executing different action, what is the maximum reward we will be able to receive? And based on that, we learn our actions or we learn our policy. So all those methods that focuses on this aspect of first learning the optimal value function, because once you learn optimal value function, it is very easy to get your optimal policy. Those are called value-based method. And most of the reinforcement learning focuses there. Most of the methods are, easily, or most of the tasks are easily mapped to value-based methods. Then I'll just directly go to something called policy-based methods. So the last one. So the policy-based methods are those methods that try to learn the policy directly instead of actually, first learning something called a value function and then from there, extracting a policy. Okay, so these are the methods, and mostly in continuous control task, right, where your actions are continuous actions, right? So if you have continuous actions, people tend to use policy-based methods more than value-based methods. And then in between, you have actor-critic methods. And these are the methods that try to combine both value-based methods and policy-based method, like the benefits from the both ends. So they also learn value function, and at the same time, they also try to modify policy or learn a policy. Okay. Right. So those were the whole spectrum of methods that I introduced you. And obviously, we're not going to go through all those methods. We'll go through one or two methods today in these sessions. Okay. So first, let us define what is a value function before going further, right? So since I'm defining value function, I hope you can get the hint that the methods that we're going to discuss are value-based methods, right? Okay. So with that, what is a value function? So there are two kinds of value function. One value function, which is defined over the state only. So this is called a state value function. And another value function, which is defined over state and action. And this is called state action value function, or sometimes we simply refer it as Q function or Q value function. Okay. So the Q represents value of the state and action pair. Okay. And otherwise, we simply have a value function, which is the state value function. Now, what is the technical formal definition? It is the value function is the expected return when you start in this state S, and after starting in this particular state S, you follow the policy pi. Okay, you follow the policy pi thereafter. Okay, so it is the expected return. What is the return? Return is nothing but your expected sum of rewards. Okay, so this is the technical term that we want to use. Okay, which we are going to call it as return, but it is nothing but the sum of reward. And why expected? Well, because in a state you can choose different action, right? So in every state, whenever you're visiting that state, you may not choose the same action again and again, right? You may choose different actions in a state. So that's why an expectation term is there. Okay. So this value function simply defines if I start in a state and then I follow some policy pi, okay, then how much reward or how much total reward I can collect by starting in that state. So what is the value of that state? Okay, so the value of that state tells me going into the future, how much of rewards I will be able to collect. Okay, the Q value function or state action value function tells us that if I start in a state and I also fix the action and I take action A, because there are multiple actions in a state, so I fix action that okay, in some state as I want to take action A only. Okay, so if I fix the state, I fix the action, then from this pair, starting in a state, choosing action A, going into the future, how much reward I can collect, okay, or how much expected reward I can collect, An expectation, because again, in other states, going in the future states, you can choose different actions. Okay, what is the total sum of rewards I can have? Expected sum of rewards I can have. That is called Q value function. Now, before we move to the next slide, just one intuition I wanted to give you. Let's say we are starting in some state S naught. Okay, this is the initial state S naught. And there are 4 actions available: A1, A2, A3, A4. Okay, and these 4 actions will take us to 4 different states: S1, S2, S3, and S4. Let's say somebody already found these value functions and have given us. Okay, so we are in S0. There are 4 actions we can choose, and we know the value of state S1, state S2, state S3, and state S4. What does the value represent? Value function of a state represent, if I go to that state, then from that state and following my current policy, how much reward I can collect going into the future, right? What is the aim of our RL method, reinforcement learning? We want to collect maximum reward, right? Now you tell me which action we will select. If I know value of all the state, then which action I should select when I'm in state S0? Naturally, I'll select the action that will take me to a state that has maximum value among S1, S2, S3, S4, right? So that is the importance of value function. If you know the value function of all the state, then from any state, you can very easily make your decision that what is the action to do, right? Because you would like to do an action which will take you to a state which has better value, which has the maximum value. Okay, and same applies for your Q function. From this state action pair, you would like to move to a state or a state action pair again, which has the maximum value. Okay. So again, same grid world that I had explained you earlier. If we try to learn Q values in that particular setting, right? This is how it looks. Okay, so these are the 2 exit states. So they have reward 1 and -1. You don't have to learn value, because once you enter this state, you'll exit the system. And these are 4 actions, and the value of all those 4 actions are written for a trial, like Q values over 100 iterations, right? So we ran some equations over 100 iterations, and these are the values we found. Once you have found these values, okay, it is very easy to find the optimal action, best action. What will be the optimal action? Well, wherever these values are maximum, that is the optimal action. So in all the state, you can see these are bold fonts, white bold fonts, and those are actually the actions that agent would like to choose in all these states. Now again, this is a toy example, but you can think about any other world with actions and everything. And once you have found these kind of values, you can automatically decide what is the best action in a state, right? So let us build on it now. Okay, so we have described what is Q value, what is the value function, right? And how does maximizing or finding the optimal Q value of state action pairs can help us to find the best action. Okay, now we just have to answer the final part of it, that how shall we learn these Q values? Okay, so I'm going to explain you what is a method called Q learning method that helps us to learn those Q values. It's a very simple method, and I'm going to explain you this method just in 2 slides. Okay, so in Q learning, we have a table which we call a Q table, right? And what are the entries of this table? So only 2 columns. In the first column, we have all possible state action pairs. Why state action pairs? Because we want to learn the value of state action pairs, right? So what would be the size of this table? S cross A, number of states into the system into number of actions into the system, right? It is simply S cross A. So we have such a table and we want to learn their value. So we have another column, which is the value column. And initially we have to initialize with some, you can also randomly initialize, but it's a better approach to just initialize with zeros. Okay. So we will have all the state action pairs and initial values as zeros. Okay. And the aim would be to update these values from 0 to some obviously non-zero values, some non-zero values in different iterations. Right? And how do we do that update? So we try to do that update we try to do that update using this equation that is mentioned at the bottom. What does this equation signify? So here you see the Q value of a state action pair. That means, from the value of this particular row, right? From time t to t+1, right? So an update will happen. So the value of a particular state action pair at time t+1 is, well, the value of the same state action pair at time t, okay? And we are going to multiply this whole quantity with something called 1 minus alpha, where alpha is something called a learning rate. Okay, so it's a value between 0 to 1 that we are going to fix. Okay, plus alpha times of this, the other part of it. What is the other part of it? Well, if you execute action A on status, what is the reward you're going to get? That is the first part. Plus another parameter gamma, it is called discount factor. This other parameter. And the maximum value, underscore this thing, the maximum value of the Q state from the next state where you're going to land, and the best action in that next state. Okay, so if it is, this equation is still little confusing, I'll explain it further in the next slide. But this single line equation is what is there in Q learning now. You take this table, you learn, you execute this equation again and again in something called episodes. Okay, and after multiple executions of these equations, the values here will start, to improve, or so they will keep on improving. And once these values start converging, we stop there. And once we stop there, then we simply see for a particular state, all the actions in that state, which is the maximum value, and that is the best action in that state. And we have learned our policy once we collect all that actions. Okay. Right. Yeah. So, so this particular video here at the center is a typical, inverted pendulum task, and that people usually do in reinforcement learning. So it's like a benchmark task. So whenever you have any method and people try to test it on these kind of tasks where there is a pendulum, which is like a free falling pendulum, and you have to make it stand like upside, upright, just by moving the base, the box at the base. Okay. Right. So here I'm trying, we will get into that equation a little more. Okay. How do we update these QSA values? So what do we do? So in reinforcement learning, there's no data set that is already available, right? I told you, right? The agent takes action onto the environment, it executes action onto the environment. So one particular interaction of the agent with the environment will have these things: the state of the system, the action that the agent has taken, the next state where the agent or the system went to, okay, and the reward that it got in the process. This is called one sample in Q learning. Okay, this is one sample or one interaction that we got from the environment. Okay, we use this sample to update our Q values. How do we update? Well, we will have some old estimate of our SA pair, right? And we will construct the new sample. Now we will construct the new sample using this interaction, right? The sample that we got from the environment. So we'll take the reward plus gamma times. Now we know this is the S dash state that we went to. In that S dash state, which action has the maximum value? We choose that QSA. In the S dash state, which action has the maximum value? We choose that QSA, right? And that creates our this new sample estimate. Okay, so we have an old estimate, that is QT. We have the new sample estimate. Okay, and then we simply sum those by this alpha based weighting. So what we say, we want, so since alpha is a value between 0 to 1, okay, so we can say that, okay, I would like to just take maybe 60% of the new sample or new estimate, and I would like to retain 40% of the old estimate, and I combine those, and that is my updated estimate. So this is how we update the Q learning. Okay, and this simple equation. So when then we are in this S dash state, again you choose the action and you keep on doing it. Okay, so you keep on doing it and you keep on updating these stable values, and I've already told you how to select the best action there. So this is what we do, and we keep on doing it again and again. So your Q table gets updated, right? And ultimately, when the values converge, when the values are not changing, you will find that, after so many iterations, the values have converged. At that time, you stop. And we can safely assume that those values, converged values, are the optimal Q values of all the state action pairs. And from those optimal values, if we choose the best action, the action with the maximum Q value, those will be optimal actions. Okay, so this is Q learning in a nutshell. There are other little more concepts involved, but I've given you, the top level view, the basic understanding of Q learning. Obviously, you can explore more, go into the algorithm and see what are the other things that I have left. But I think those will be easy to understand. Okay, right. Now, in Q learning, I showed you we create this table of Q values, right? But what will happen if the size of the table is too large? Like here, few examples are given, right? Few game examples are given, right? These are not real situations. These are only games, that too board games. So if you see, there's a game called backgammon, and number of states in that game is 10 raised to power 20. This is the number of states. You multiply that with number of actions and then think about the size of the table. Maybe your RAM won't be enough to fit that whole table. Right? You see, chess has 10 raised to power 46 state. This game of Go I was telling you about, it has 10 raised to power 146 state. And if you have continuous state like a UAV, if a helicopter or a UAV is flying, the state space will be a continuous state space. Right? How do you store that continuous state space in a table? Right? So that creates a big trouble. So we learned a very good algorithm, but we'd like to generalize it, right, to all the situations, right? But it is very difficult to generalize even for games. How do we generalize for real situations? Okay. So what is the answer to that? The answer is we generalize based on, I'm giving you a minute to think about it, right? So we generalize based on maybe similarity of the states, right? Or maybe based on maybe grouping the similar situations and similar states together. So if we learned a value of a state and there are so many neighboring states, right? Then the value of neighboring state will be very much closer to that state value that we have learned. So can we generalize? Like maybe we learn the value of one state and then we try to interpolate or extrapolate to other very similar state or similar situations. And this particular generalization is basically the idea of all machine learning. In machine learning, what do? You take a training set and then with the set of parameters, you want to learn a set of parameters from that training set, right? So that you can generalize for all possible testing set. Now, when you do machine learning, your training set is like 70% and testing set is 30%, but these are only samples of the real world, right? So for a trained machine learning model, right, the actual test set is the whole outside world, right? Which would be much, much larger than your training set. So what you're trying to do, you're trying to generalize from a small training set to all possible test sets that are available there. We have to apply some similar concept here. Okay, and we do that by something called function approximation. Okay, so in what do we do in function approximation? Instead of learning the QSA value for each pair, okay, can we transfer that problem into learning a set of parameters W for that Q value of that pair? Okay, so that means using a set of parameters in a function, we should be able to approximate the Q value of that state action pair. Okay, the simplest example of doing this is using a linear function approximation. So let's say now we have, let's say, some set of features for a state action pair. And there are 2-3 features maybe. Okay, and then we design a parameter vector. Okay, so let's say if you have feature F1, F2, and F3 for a state action pair. Okay, we multiply some parameter W1, W2, W3 with the feature F1, F2, F3, and we sum it. That is what is written here, right? And we are saying that this function that we just created, linear function, approximates the value of any state action pair, because any state action pair will have these 3 features. And if we have the correct, or if you have learned the correct parameters, W1, W2, W3, we can always calculate, because these Q values are numbers, right? So we can always calculate using this function. So this is a great advantage, because now if your size of QSA table is in, let's say, in lakhs or in crores, right? Now I don't have to store those lakhs and crores of values in a table. Instead, I will just focus on learning these W parameters, W1, W2, W3. And if I found the best W1, W2, W3, right, these W parameters, then for any state action pair, I'll take the feature values, multiply with the parameters, and I have the QSA. I have the value function, right? So what we just did here, we transform the problem from learning all the QSAs to learning the parameters that can help us to calculate those QSA values. Okay, great. And this is where deep reinforcement learning or deep learning models actually is the great benefit, or has actually helped the field of reinforcement learning to to have very good, superhuman kind of performance in so many tasks. Okay. So before we delve into, so this is the final part of today, this lecture, right? So we'll touch upon these a particular kind of deep reinforcement learning model called deep Q networks, wherein basically whatever we learned in Q learning, now we want to transform that into a deep learning based setting. So before I delve into that, right? Sorry. Let me give you a very, bird eye view into deep learning, as I understand it. You can have your own views, definitely, and maybe my understanding may not be enough, but this is what, as I see deep learning. Okay. So usually what happens in a typical machine learning task, if you forget deep learning, okay, in a typical machine learning task, you have an input. Okay. From that input, there is always a module which extract features, right? Like for this image of a car, the features would be maybe how many circles are there, how many edges are there, right? So these could be features, right? So in a machine learning task, you take the input, you extract features, and then the learning of parameters happens over the features or the feature that you create, right? And once you learn the parameter, then you perform your task, whether this image contains a car or not a car, right? That is the final output. Now, this feature extraction is a very tedious job, and many times people, handcrafted features, right? Because nobody knows what are the perfect features to learn anything. Means this whole feature extraction comes from domain experience, many years of expertise if people have in a particular domain, and then they give you some heuristics that these feature will work, this feature will not work, and all that. So this feature extraction was always a tedious task for the typical machine learning methods. Now what deep learning helped is it actually combined this feature extraction and the classification on your learning task together. It fused it together. Okay. And instead of, calling it feature extraction, the process or the module actually become a feature discovery task, right? So what happens in feature discovery, or what we mean by feature discovery, now given an input, you do not have to specify what are the good features or what features to extract, what features not to extract. Okay. You put maybe a CNN based model. Okay. And obviously at the end, your own task, classification, regression, whatever task you have, you combine them together in a single backbone. And then you perform, or you correct those, or you see the error at the output, and you back propagate on that. With this process, these layers, these CNN layers, could automatically discover which features are important for this particular task. And that was a great boom, right? So now you no more have to look for what features are good or what features to extract. The model itself performs that task, right? So this is the bird's eye view of deep learning. Okay. And I hope you're getting some hint that how deep learning is going to help reinforcement learning, right? So basically now we would like to extract features out of our state, where our state could be anything. right? So in a typical Q learning, what we were doing, we were given state and action pairs. We created this table and we were learning the Q values. Now in deep Q learning, given the definition of a state, where the state could be an image, the state could be any, description of the environment, right? We'll put a deep model, right, which will extract the features, and also maybe it's a regression task here, you can see, and we would expect from this model to tell us the Q value of all the actions that can be performed in that state. Here the actions are discrete. For continuous actions, there are different models, but we're assuming the actions are discrete. Now, if I learn these kind of a deep Q model, then for any state, I can always find what are the Q values of all the action, and I'll just choose the max Q value action, right? And that max Q value action, we have already established that fact that is going to be the optimal action in that state. Now, given a state, whatever big, maybe complex state it is, if I'm able to train this very nice deep model, I must have learned the optimal policy. Now, how to train this model? Because there's one thing that is missing. What is that thing? Well, in a typical machine learning task, you know the ground truth values, you know the ground truth levels. So you can calculate the error function or the loss function on which you can back propagate and train your network. But here, since we have to decide what is the best action, who is going to tell me what is the ground truth? Because nobody knows the ground truth, right? We are learning on that task by experiencing or by interacting with the environment itself, right? So that is one tricky part that we still need to solve. Okay. And the first attempt on this particular kind of solution was done using these kind of Atari games. So if you remember these very old Nokia phone kind of games, right? This one is a breakout where there is a slider at the bottom, and then you have to score maximum point by breaking this wall, or this like a ping pong, right? So the researchers in Google's DeepMind lab, right, they thought that can we develop a single reinforcement learning method, or can we develop a single algorithm that automatically by itself, without giving any extra information, can learn how to beat humans, or can learn how to achieve maximum score in these kind of games. These are very different games that are available, because for human it is very natural. If you play these games for 10 to 20 times, you will become an expert automatically. Nobody will tell you any trick. Can computers learn that thing? Okay, and the information that we have is this interface, this screen. That is the only information available. That is your whole state space. Okay. So these are the initial two works that came by Min et al. So the initial paper came in 2013 in NIPS, and then they had a publication in Nature in 2015. So what, 6 to 7 years now, right? So now it's getting old. Where they actually showed that how deep learning and reinforcement learning can be linked together, and actually that evolved the whole deep reinforcement learning settings, which are now very popular. Okay, so we'll see this particular model that they had proposed. Okay, and the name that they put for the model is called deep Q networks. Okay, which was basically the deep neural network for Q value function approximation. The task is still the same. You want to do the value function approximation with a set of parameters, but those set of parameters now are the parameters of your deep network. Okay, I told you they did not use any prior knowledge. It just those screen, these kind of screens that were used. The actions were these joystick inputs, right? Because it was all about the games, right? So whatever inputs are available on the joystick, and that's why the actions are discrete here. Okay. They also removed all the color information from these frames, and they used a sequence of 4 frames to represent a single state. Why a sequence of 4 frames? Because you see in all these games, there is something moving always, right? How do you capture those movements? So from a single frame, you won't know that where is the vector, right? In which direction the ball is going, or in which direction the slider is going, right? So to capture that, they had a sequence of 4 frames, and using the 4 frames, if you see it, then you will find that where the ball is moving and all that, right? So they used the sequence of 4 frames to represent a single state. Okay. And since all these games had different scoring mechanisms, right? Somewhere the score for a point is +10, somewhere it is +100, somewhere it is only +1. So now to normalize that, what they did is all the rewards in all the games were plus or minus 1, right? So they normalized all the reward across different games to avoid any scaling issues. Okay. So they designed this kind of a deep model. So this is where this is the DQN model that they designed, and every basic DQN model from today's standard, if you see, right? So they had, so this was a sequence of 4 frames. Then they had these actually 3 CNN layers, only 2 is shown here with ReLU activations, and then the fully connected layer, and finally the value of all the actions. So they had 16 or 17 actions depending on the game, right? Oh, sorry, 18 actions. Okay, depending on the game. Right. So here are more details about their model architecture. You can see, right? CNN layers. So I'm not in detail of these layers, right? So because I think that will be the topic for another talk on deep learning, right? But I wanted to show you the architecture, the end-to-end architecture, the way it was. Okay. Now that problem still remains, right? We don't have the ground truth value. How we are going to calculate the loss function and learn on it? Right. So they also had the same issues, and that's why they ran into something called these stability issues of DQN. Like initially their model was not at all convergent. Okay. So why? First thing is the data is sequential and successive samples are correlated. So this usually when we use data for any machine learning training, we assume that the data are IID, right? Independent and identically distributed data points. But here, if you see, we collect samples, we execute an action, we go to next state, then execute an action, go to next state, execute an action. Go. So all the successive samples are very much correlated with each other. And because they are very much correlated with each other, it became a problem for our deep model. So their deep model was not converging, it started diverging. So that was one problem that they faced. Second, a small change in the Q values was making the policy to oscillate. What is the meaning of that? Well, what we said that, you know, we will choose the action where the Q value is maximum. Now this max function will not even differentiate at up to 10th decimal point also, right? So even between two Q values, if one Q value was higher for some decimal points, right, then that Q values action will be chosen as the best action. And in the next iteration, right, if, because, you know, it's a deep model, so many these decimal values will fluctuate a lot, right? But it will change the policy completely, right? So in the first iteration, this action was better. Then in the next iteration, this action became better. And the difference between their values is just in some decimal points. That became a problem because then the policy was not stable. It started oscillating because if you see the policy, it tells you what action to take in each state, and that was changing every time, right? So that became the second problem. And obviously the scale of rewards was a problem, but they solved it using this clipping the rewards. I already told you, they said all the rewards is between +1 and -1. So how did they solve the first two problems? Okay. So, so in order to do that, first thing they did is, instead of using a single network, this DQN network, they used two DQN networks, which was the copy of one another. First network they called the basic Q network, or you can say the learning network, where all the learning will happen. And the copy of that network, they called it a target network. Okay. Now, what was the difference between these two networks if both were copy of each other? Well, in the target network, they froze the parameters. So what is the meaning of freezing the parameters? That means they were not updating the parameters of the target network. They said that, okay, during a learning cycle, right, during each epoch, only the Q network's parameters will be updated and target network will remain as it is. Why did they do that? I'll show you in the next slide. Then they use something called experience replays. Experience replays, you know, the term itself has the concept in it, right? So what is an experience here in reinforcement learning? All the samples that we collect from the environment, right? State, action, state and reward, right? Next state and reward. So what they did is, instead of whatever these experiences or interactions we are receiving from the environment, instead of just executing that, they started storing it into some buffer. And then from that buffer, they were randomly sampling a mini batch and use that to train the deep network. Why they did this? This is what they called experience replay. And why they did this? To break that. I hope you got the answer, right? So they did this to break that sequentiality of this state action or the samples that we are receiving, right? So they wanted to make their samples IID, right? So once they are doing this random sampling of these stored experiences, that helped with that. Okay. Right. So let us now again revisit why they created two separate networks. So I told you there was no ground truth available, right? I think I can better tell you, yeah, with this equation. Now, since there was no ground truth available, right? How to train the network? So they use something called the TD error, which is basically, so if you remember, this was the new sample estimate that we were creating, right? While learning the Q values, right? While updating the Q values, reward plus gamma times max. So this was the new sample estimate. And we are combining the new sample estimate with the old sample estimate. Here, with this new sample estimate, okay, they were deducting or subtracting the old estimate. So they say, oh, this is the new estimate, and this is my current estimate, QSA, from this theta is my network. So from the new estimate, if I subtract my current estimate, then that gives me error. This we usually call the TD error. Okay. The problem with this equation was that this QSA in the target was also coming from the same network from where you're choosing your current values. And because both are coming from the same network, both Q values, that means your targets are biased. Means by the time you update your parameters to achieve the ground truth or this target value, the target also already changes because you're updating those parameters. To fix that, what they said is, okay, let us create a separate network and we'll fix the parameters of that network and we'll use the Q value from that network. So that is being shown here, with this minus sign over the theta. Okay. And with this, now this target becomes stable because reward is not going to change for every state action pair. That is stable. And Q values will also be stable, at least for at least few epochs until we are changing the target network. Okay. So this is what they used in order to make stabilize their whole learning. Right? And this is very important concept. And after that, all the deep models that came after this paper, they used this concept. Okay, so this is at the very core of your deep reinforcement learning models. Second was experience replay. I already told you, right? So this state, action, reward, and next state is basically one experience, one transition, right? And in order to break that correlations between the samples, they stored these transitions into a memory. And in order to train the network, okay, they use this mean squared error over this TD error, okay? In order to train the network, what they did is from this replay memory where they were storing the transition, they sampled a mini batch. And then since it is a randomly sampled mini batch, then the samples won't be correlated and they use that for training the network. Okay. So this is the whole model. I have given the reference of the paper at the bottom. I don't think we have enough time to go through every line of it. I would be happy actually to go through this algorithm line by line, but if you have understood whatever I discussed in the previous slide, then going through this algorithm would be very easy. You would be able to understand every line of it. Okay, it's the same thing written in a pseudocode manner, whatever we described earlier. Okay. So this was the deep Q model or deep Q network model. Okay. Now let us see what took to train such a model. Creating a model is one thing, training that model, deep models is another thing, right? So they trained it on, they very nicely write 49 Atari games, and that somehow gives you a question that why not 50 Atari games? There are more than 50 Atari games available. Why this typical number of 49? My assumption is maybe they got good results on 49, but I'm not sure about the exact reason. Then they used this RMS prop with mini batches of 32, and they used 50 million frames. And their training time was almost about 1.5 months. So deep RL models are not easy to train if you're directly learning from the matrix of pixels. You can see that the training time is huge. But again, they trained a single algorithm on 49 different games, right? An algorithm that becomes an expert on all these different kinds of games. Okay, and then other information is given. And for evaluation, what they did, so their trained model, it plays every game for 30 times for 5 minutes, and then a human also plays the same game, and then a random agent plays the same game, and then they rate that with respect to the random agent, okay, how well did the human perform and how well did the agent perform. And these were their results. Obviously you can see like the blue bars here show the performance of the DQN model, and mostly the DQN model was performing much better than what a human performed on those games, right? But again, there were few games where improvement was still pending, like maybe like there was some aspect of improvement, and those are already improved now. Okay, so in last 5 years, so many better models have come based on DQN model, which has improved to 50-55 these Atari games. Okay, so yeah, this is deep reinforcement learning. And if you want to start with reinforcement learning to get the basic concepts of reinforcement learning and everything, then I think this is a very good book by Satin and Bartu of reinforcement learning second edition. You can follow this. And these are the two papers that I discussed. So not this paper, Mastering the Game of Go, but if you go through this paper, the second paper, you'll find that they've used a lot of reinforcement learning here as well. More complicated, deep reinforcement learning. So with this, I think I'm at the end of my allotted time. So thank you. Yeah, so this is my email. And obviously, if you have any query regarding reinforcement learning, or you want to connect to discuss more about reinforcement learning or any use of or application of reinforcement learning in any domain, I'd be happy. Okay, so you can always connect to me over my email. So with that, I think I'll stop here. And if there are any more questions, I'd be happy to take them. So over to you, Dr. Ashok.
Thank you. Thank you very much, sir. And that was really wonderful from basic mathematical things which is being involved there in deep reinforcement learning and how it differs from the deep learning. That was a very well explained presentation from your side, and definitely it was a brush up at my end, because already I had gone through all these things, and my concepts are now going to be more sound after this talk. And let me see the participants. If you have any queries, you can put on the chat window, and Dr. Arun can see on the live YouTube live streaming that if there are any question or the chat window, they can put it on the here in Zoom, so that sir can answer. Please, Dr. Arun, please look into the YouTube streaming.
Sir, I'm not. Sir, there is no query onto the YouTube portal.
Fine, that's fine. That's fine. It me
Great.
because things were really so simple and very well explained. They may not be having any query, but definitely this is the new thing we can see into the deep reinforcement learning has a larger application in upcoming 5G or 6G, as I have gone to a lot of literature. So definitely it's going to be very, very useful for us, and the implementation by looking into the real-time problem and mapping them with deep reinforcement learning will definitely help us. And yes, that's really fine. That's really nice. So definitely, sir, we will look into, and we will be definitely reaching to you again if in future we need, because definitely we require your experiences in this area for our young researchers. So those who are at the beginning of their research, they can definitely do the things in a much better way. So once again, on behalf of Department of Computer Science, University of Jammu, and TLC Teaching Learning Center, Ramanujan College of Delhi University, I thank you. I extend my thanks to you for your kind acceptance and coming here to deliver a talk. That was really wonderful. And in future also, we will be keep associated with you, sir. And that's very nice. So Dr. Arun, would you like to add into it? Dr. Arun, my counterpart from Delhi University, is there, sir. Dr. Arun, please go ahead.
Okay.
Thank you, Dr. Shashi Shekhar, sir.
Yeah, thanks for having me.
Thank you. And that was really a very nice session, informative one. And there's one more information that I need to share with you. The course is self-paced course, so students will be uh, watching this video. This is actually a YouTube recorded video, and they can
Okay.
view at any point of time. So if in case there exists some query, so we can definitely get back to you,
Oh,
sir.
sure. I will be happy to answer those. Great. So thank you, Dr. Ashok, Dr. Arun, for having me for today's talk.
Yes, sir.
Uh,
Thank you, sir. Thank you once again.
Thanks a lot, sir. We will keep in touch. Thank you very much.
Ashok, sir, can you please stop the